Hello and welcome to my YouTube channel. Today we shall be discussing on the scalar triple product of vectors. But before now, we've discussed on two other kinds of product, namely the dot and cross product of vectors. So I suggest you please watch those videos before coming back to this one. Okay, so given three vectors A, B and C, so the component of vector A are A1, A2, A3, vector B, B1, B2, B3, and vector C, of course, C1, C2, and C3. Now we will write the scalar triple product of vector A, B, and C as vector A dot vector B cross vector C. So this quantity we shall call the scalar triple product. Scalar because when you compute this, this guy, it gives you a number which we call a scalar. Triple in the sense that this product involves three vectors A, B, and C. So the value of this scalar product or scalar triple product is given by the third order determinant as follows. How we compute this is a third order determinant. So the first row of the determinants will be the components of vector A, which are A1, A2, A3. The second row of this determinant will be the component of the second of this vector B, B1, B2, and B3. And the third row, C1, C2, and C3. So the scalar triple product of vectors A, B, and C is given by this determinant. Of course, this can be proven, but I don't want to do that here. So let's take one quick example to illustrate this. So example, find the scalar triple product of the vectors. A is 2i minus 2j plus k, vector B, I plus j minus 2k, and of course vector C is given as this. So very quickly, the scalar triple product is given by, so we have A dot B cross C. So this quantity defines represents the scalar triple product. Is equal to the third order determinant whose entries are the components of the three vectors A, B, and C. So the first row, vector A, 2, negative 2, and 1. So 2, negative 2, and 1. Second row, vector B, 1, 1, and negative 2. And the third row, minus 1, 2, and 1, minus 1, 2, and 1. And of course, this object is familiar from cross product. So we now calculate this 3 by 3 determinant using the Cramer's rule as we've been doing before. So recall your signs: plus, minus, and plus. Determinant of 3 by 3 matrices. That's the topic. Okay, so we can calculate this. So we pick the first entry here, 2, and then reduce to 2 by 2 determinant by deleting the entries of the row and column of 2. So what do we have left? We have 1, negative 2, 2, and 1. The next entry is negative 2. And what sign is that? Minus. So that is minus, minus 2. We'll do the same thing. Delete the entries of the row and the column. And what do we have left? We have 1, negative 2, negative 1, and 1. And the third one is 1 plus 1. The same thing, we delete entries of the row where 1 is and the column. And what do we have left? 1, 1, negative 1, and 2. So we now have, we have reduced the 3 by 3 determinants to a group of 2 by 2 determinants. So this gives us, so this is 2, determinant of 2 by 2 matrices, we now know. So 1 times 1 is 1. 1 plus 4. Minus times minus is plus 2. 1 times 1 is 1. Minus 1 times minus 2 is 2. Minus 2 plus 1 into 1 times 2 is 2. Minus 1 times 1 is minus 1. So this is plus 1. So this gives us 2 into 5 plus 2 into minus 1 plus 1 into 3. So 2 times 5 is 10. 2 times minus 1 is minus 2 plus 3. So 10 minus 2 is 8. 8 plus 3 is 11. So given three vectors A, B, and C with the components here, the scalar triple product A dot into B cross C is equal to what? 11. Now we shall investigate a few important properties of the scalar triple product. Number 1, the scalar triple product does not change by changing the vectors in a cyclic order. That's the key word there, in a cyclic order. So let me explain that. So we have vectors here, A, remember 3 vectors, B, and C. Okay, now that's the first order. Now if we want to rearrange these vectors in a cyclic order, the next set of vectors here would be, so let me write it this way. Let me go again. A, let me write it like this, B and C. The next set of vectors here in a cyclic order, here we began with A, the next one is B, will now be B, and then C, cyclic, and then what? Vector A. And the next one will now be vector C, so C, A, and then vector B. This is what we mean by cyclic order. Okay, so A, B, C is the first cycle. The next cycle is B, C, A. The third one is C, A, B. So these are the 3 possible, cyclic orders we could have from this vector, these 3 vectors: A, B, C, B, C, A, C, A, B. Now what we are saying here is that the scalar triple product, which we know, which is A, dot B cross C, doesn't change by changing the vectors in a cyclic order. Now look what we've done here. So we are now saying that we can define the scalar triple product here as follows. This is A dot B cross C. That's the scalar triple product. Now we now start with vector B, the next cycle. So this will now be B dot C cross A, and the third one is C dot A cross B. What we're saying is that these 3 quantities here will give us the same result of scalar triple product. So the scalar triple product does not change. This result will not change by changing the vectors in a cyclic order the way we've done. So A dot B cross C, B dot C cross A, C dot A cross B will have the same result. So if you're asked to compute or find the scalar triple product of 3 vectors, you are free to use any of these cyclic orders to find such a value. That's the first property. Number 2, if the scalar triple product, which is this, is equal to 0, then it will mean that the 3 vectors A, B, and C are coplanar. Coplanar simply means that they are on the same plane, they lie on the same plane. They are coplanar, something like this. So we have vector A, vector B, and vector C. They are on the same plane. Otherwise, they will be on different planes. Okay, we'll talk about planes probably in the next 3 videos. So what we're saying here is this: if 3 vectors A, B, and C are on the same plane, now their scalar triple product will be 0, and vice versa. That means if the scalar triple product of 3 vectors is 0, it tells you that the 3 vectors are coplanar. Coplanar simply means that they're on the same plane. So if you're asked, for example, in an exams, to show that 3 vectors are coplanar, what do? You compute their scalar triple product, and that should give you 0. So whenever you compute the scalar triple product, like the one we did before in that example, and your answer is 0, this tells you that the 3 vectors whose triple product you've computed are coplanar. Number 3, the absolute value of the scalar triple product. So we have the absolute value, which is, so we have A dot B cross C in absolute value. That's what I was saying. So the absolute value of the scalar triple product gives the volume of a parallelopiped, spanned by the vectors A, B, and C. Now, if you recall, in the case of cross product, we had I had explained and also proved that that the area of a parallelogram, spanned by 2 vectors A and B, is given by the absolute value of the cross product. So here I'm saying that the absolute value of the scalar triple product gives us this time the volume of a particular shape called a parallelopiped. Okay, now a parallelopiped is a three-dimensional figure, with 6 faces, and each face is a parallelogram. So I'm going to show that to you here. So let us see how we can prove this. So we have 3 vectors given. So let's look at this. This is my vector A. Okay, vector A. And then this is vector B. This is vector B. So I want to define my third vector, vector C. So vector C is a vector somewhere here. That is vector C. Okay. Now, as you know, if we make a copy of vector B and A, we get a parallelogram that is spanned by vector A and B. So, good. All right, that is it. So this is a parallelogram that is spanned by vector A. Sorry, yes, I'm correct. Spanned by vector A and B. So let's go ahead and make copies of vector C and other copies of vector A and B. So if we make a copy of vector C here, we'll get this. Another copy of vector B, we'll get this. Vector B, C again, something like this. We'll now make vector C again from here. We'll get something like this. Okay, so that we can now get this. Good. So if we make another copy of vector B, and whoop, and that is it. So this is a shape which we call a parallelopiped. So you see that it has 6 faces, 1, 2, 3, 4, 5, 6, and each of the face is what? A parallelogram. So this is called a parallelopiped. Okay, so we want to show that the absolute value or the magnitude of the scalar triple product of 3 vectors A, B, and C will give us the volume of this parallelopiped. All right, let's proceed. Now, if we calculate the volume of this shape conventionally, what do we do? So we say volume. What the volume would be? What? The base area times height of the parallelopiped. So the base area simply refers to this area here. So that's the base area. This vector C, let me write it here. So that's the base area. So the base area there, so volume will just be volume V. I want to write as V is equal to base area. So that the area here is the area of a parallelogram, which is what? Which is the cross product of vector B and C, if you recall. So this area here is simply the cross product of vector B and vector C, if you recall. If you like, in absolute value, but let's leave it like that for now. So the base area of this parallelogram spanned by vector B and C is simply, the cross product of vector B and C. Of course, it will be in absolute value, but I'll just leave it for now, since I'll bring it in at the end. So times height, height is h. But here, the height is not defined. So let's bring in the height. So if I drop a broken line from this point, so this makes a right angle here. So that is the height. So before then, so let the angle between vector B and C, say, let that angle be angle alpha. So that when we drop a height at this point, we call the angle that is formed here angle theta. So that this line here is h, which is the height of a parallelepiped. Now, the base area, which is a cross product of vector B and C, if you recall, the cross product of 2 vectors B and C is a third vector, which is what? Which is perpendicular to the 2 vectors. So the cross product, so this is the cross product B cross C of vectors B and C, if you recall. So this vector here will be the cross product of vector B and C, which is the area of which is the base area the area of the parallelogram spanned by vector B and vector C. And so we observe the following, that this vector B cross C is parallel to the height of the parallelepiped, which is H. Okay, so what do you see? You see that a Z angle is formed here. So if this angle here is angle theta, this angle here is also what? Angle theta. Reason is that alternate angles are equal. So let me just magnify what is happening here out here. So we have this as a cross product of vector B and C. So we have this, and we have this as the height of the parallelepiped. So this is H, this is angle theta. So we are saying here that this angle here also is theta, since these two angles are what? Alternate angles. So we proceed. So we can, so let's work with this, with this shape. So what I have here is what I've, enlarged, magnified to this point. So what is H? So this is my vector A. Remember, this is vector A. So adjacent and hypotenuse. So we can find H. So we can write cos theta because of this angle. So the cosine of theta is equal to adjacent is H all over hypotenuse. Hypotenuse is A, vector A. So we can make H here the height, the subject. So we have H is equal to vector A times the cosine of theta. So we can go back here to our volume formula and replace our H with A cos theta, so that the volume of the parallelepiped then becomes B cross C times H. What is H? H now is A, the cosine of theta. So of course we can write this. We can put vector A first. The same thing is a dot product, so it's the same. I can put vector A first, A dot B cross C, the cosine of angle theta. Now, if you recall from dot product, we had defined that the dot product of two vectors A and B is given as what? The length of vector A times the length of vector B times what? The cosine of the angle between vectors A and B. So the length of vector A times the length of vector B times the cosine of the angle between A and B gives us what? A dot B. And let us relate this, what we have on the right hand side here, with this. So we see that if we compare these two things, so this is vector A, and where you have vector B, what do we have? You have B cross C. So if this length, if what you have here is A dot B, so what you have here must be equal to what? This will be equal to A dot B cross C. So this product here is nothing but what? The dot product of vector A and B, of vector A and vector B cross C. So we're having here the dot product of vector A, this vector A, and vector B cross C. So the angle between vector A and vector B cross C is theta. So we define this dot product of B cross C as what? As vector A times vector B cross C times the cosine of what? The angle between them, which is this. So A dot B cross C cos theta is nothing but what? The dot product of vector A and vector B cross C. So what have we seen? We have seen here that the volume of the parallelepiped is equal to A dot B cross C. And we said this volume should be given, this quantity should be put in absolute value. So when you compute this, what you have is the volume of this shape, which we call a parallelepiped. Let's take one example to illustrate. Example: what is the volume of a parallelepiped spanned by the vectors given A, B, and C with the components as follows? So this is very easy. So solution, what do? You simply compute the scalar triple product of vectors A, B, and C and find the absolute value. So this is what the 3 by 3 or the third order determinant, where the first row is a component of vector A, as we've done before. So this is -2, 5, -2. The second row of vector B component 1, 2, and -1, and the third row are the component of vector C, which are 2, 2, and -3. So I leave this to you to confirm, to verify that when you compute this cross product, when you compute this determinant, what you get is 17. So this is already a positive number. So let's just go ahead. So the absolute value of the scalar triple product is absolute value of A dot B cross C, absolute value. That gives us the absolute value of 17, which is what? 17. So this absolute value here helps to knock off a negative sign that might come from the determinant. All right, so we have this. That's it. So the volume of the parallelopiped, which is spanned by these three vectors, is what? 17. So if you go with the formula base area times height, the answer will also coincide with what you have. I hope you understood the lecture. Please kindly subscribe to my channel if you've not done so already, and share, like, and comment. Thank you, and bye-bye.